Have you ever wondered how anything could begin if there was no before for it to rise out of? The thought slips quietly into your mind, unsettling and fascinating at the same time. If the universe had a starting point, what was waiting on the other side of that boundary? Was there a silence older than time, a space without dimension, a kind of existence that doesn't fit into words at all? That single question opens a soft crack in reality, inviting you to lean closer and listen. Welcome back, traveler. Tonight we drift through science. You're here, in your own space, maybe lying on your bed with the lights dimmed, or leaning back on a quiet couch while the night wraps itself around everything. Your room has its own gravity right now, gentle, familiar. And if these calm journeys through the cosmos bring you comfort, I'd be truly grateful if you left a like and subscribed, so more people searching for rest can find this quiet corner too. And if your thoughts have been restless today, or if your mind is heavy with things unsaid, it's all right. You don't need clarity. You don't need focus. You're not here to solve the universe. You're here to be carried through it. If your attention drifts, that's fine. If you fall asleep halfway through, that's even better. You're allowed to rest without holding on to every idea. You're allowed to let the questions pass through you like light moving across water. Tonight, we'll wander gently through the frontier where cosmology meets mystery. We'll explore scientific attempts to understand the pre-Big Bang landscape, ideas shaped by quantum fields, bouncing universes, invisible symmetries, and mathematical scars left behind by the earliest moments of expansion. And between these cosmic theories, we'll glance at the human side. Observatories humming in cold deserts, researchers puzzling over faint radiation maps, simulations crashing, data being recalibrated, and long nights spent chasing hints older than space itself. So as you settle deeper into the quiet of your room, we'll step softly past the edge of the universe's first moment and drift into the territory before beginnings, where time loosens, meanings blur, and imagination becomes your map. Let the darkness around you feel safe and familiar as we move forward. You don't have to do anything now. Just sink a little deeper into your pillow, relax your shoulders, and let the journey begin. You're lying there, letting the quiet settle over your room, and as you drift outward into imagination, you find yourself floating at the edge of time itself, a dim, horizon-like boundary stretching across a dark landscape. It feels solid in a way that horizons never should. Behind you lies everything familiar: galaxies, atoms, light, motion. Ahead of you lies something you can sense but not quite enter. The air around this boundary feels strangely still, like the world is exhaling but hasn't yet taken its next breath. Physicists call this boundary the cosmic horizon of the early universe. It's not a wall of matter or a curtain of dust. It's a limit created by the fact that light, temperature, and density were once so extreme that space-time itself behaved differently. Before about 10:43 seconds, the Planck time, our laws of physics stop working. Not because something mystical happened, but because our equations simply cannot describe conditions that dense and energetic. That number, 10:43 seconds, is the smallest time interval that makes physical sense in our current theories. Below that, gravity and quantum mechanics collide in ways we can't yet reconcile. Imagine trying to calculate the weather inside a black hole using ordinary meteorology. The tools break before the truth does. And so, the beginning of the universe becomes a kind of mathematical silence. In labs and observatories around the world, researchers try to push into that silence. They build particle accelerators that smash protons together at near light speed, hoping to recreate the energy scales of the early universe. Each collision sprays detectors with showers of particles. Scientists hunch over monitors, comparing the traces with predictions, searching for new symmetries or unexpected anomalies, anything that might hint at the physics that ruled before our equations could speak. The early universe is often imagined as a sea of blinding brightness, but here, at the threshold, you feel something quieter. It's like standing at dawn before the sun breaks the horizon, sensing the world holding its breath. The universe, before its beginning, feels less like violence and more like potential, an unlit room waiting for a switch you cannot see. This boundary raises a disorienting idea. Perhaps before is a word that stops making sense at this scale. Time as you understand it, past leading to present, leading to future, may not have existed in the same way. Asking what happened before time begins is like asking what's north of the North Pole. It's a question that dissolves when you reach the place you're asking about. And yet, physicists don't give up simply because a question feels paradoxical. They create new mathematical frameworks. They rewrite assumptions. They test the limits of quantum theory. They look for clues in the faint afterglow of the Big Bang, the cosmic microwave background, or CMB. Satellites like COBE, WMAP, and Planck have spent years mapping that ancient light with exquisite precision. The CMB reveals tiny variations, temperature ripples 1 part in 100,000, that show how matter clumped together over billions of years. These ripples are like fingerprints left by physics that unfolded before the universe cooled enough for light to travel. Scientists sit in dim rooms, staring at color-coded maps of these ripples, adjusting parameters, wondering whether some feature might be a clue from a time before time. You imagine floating closer to that boundary again. It doesn't feel like emptiness. It feels thick, as though everything that would later become stars, galaxies, planets, and you had been compressed into something much denser than thought itself. Not matter, not space, not time, just a raw, undefined something, like a note held so long it becomes indistinguishable from silence. And as you drift, you begin to sense why this question has captivated physicists for so long. It forces them to confront the limits of understanding. Humans can study stars billions of light years away, detect gravitational waves from merging black holes, and measure particles far smaller than atoms. But ask what the universe emerged from, and even the greatest equations fall quiet. Some theories suggest the early universe passed through phases we can barely imagine, periods of quantum foam where space and time flickered unpredictably. Others propose an earlier cosmos that contracted before bouncing into the one we know. Yet others suggest a timeless state, where quantum fields fluctuated in a way that eventually triggered expansion. All of these possibilities arise because the universe leaves traces behind. Like footprints in sand, the afterglow of the Big Bang and the distribution of galaxies carry imprints of whatever came before. Researchers use supercomputers to simulate trillions of years of cosmic evolution, watching virtual universes rise and fall, comparing them with the one we see outside our windows. The simulations fill vast rooms with stacks of servers humming quietly in the dark. Scientists walk between them like gardeners tending orchards of possibility. Sometimes the simulations reveal hints of new physics, unexpected density fluctuations, strange patterns in virtual CMB maps, behavior that doesn't match standard cosmology. These anomalies send teams back to the chalkboard to adjust assumptions, searching for the hidden hand shaping the first moment. You drift through these possibilities, feeling the strange beauty of not knowing. It's comforting in a way to realize that even the universe has places where the rules blur. The beginning of everything isn't a clean line. It's a zone of uncertainty, a shoreline where familiar physics dissolves into something we're still learning to describe. And maybe, as you rest there in the soft quiet of your room, this uncertainty feels less like a threat and more like an invitation. Not everything needs a definite answer. Some mysteries are meant to stay open long enough for you to find your own meaning in them. Yet the question lingers, glowing faintly like a distant lantern. If the boundary of time is not a wall but a veil, what might lie beyond it, not as a contradiction, but as a deeper layer of existence, quietly shaping what came after? As you float deeper into this strange pre-cosmic landscape, you find yourself surrounded by a kind of darkness that feels alive, not empty, not still, but quietly humming with possibility. It's unlike any night you've known. There are no stars here, no distance, no direction, yet you sense subtle flickers, like tiny sparks rising and disappearing before your mind can fully catch them. It feels like standing inside a room where something is about to happen but hasn't yet chosen its shape. Physicists call this realm the quantum vacuum. In everyday language, vacuum means empty. But in quantum field theory, emptiness is more active than fullness. The vacuum is a seething ocean of fluctuations, invisible and constant. Particles appear and vanish, pairs form and annihilate, fields rise and fall. Even at absolute zero, the vacuum refuses to sit still. The universe cannot be perfectly quiet, not even when nothing is supposed to exist. One of the most surprising facts is that these quantum fluctuations have measurable energy. Experiments like the Casimir effect proved this. In that experiment, two metal plates placed extremely close together feel a tiny force pushing them together, not from air, not from particles, but from fluctuations in the vacuum itself. This force is tiny but real, showing that nothing has weight. In dim labs, researchers control vibrations, cool equipment to near absolute zero, and isolate metal plates from external noise. They adjust lasers and sensors, recalibrating again and again. When the plates drift slightly toward each other, they smile or sigh, depending on whether the signal rises above the background noise. These delicate experiments offer a glimpse into the behavior of nothingness, revealing that it is far from empty. You imagine the quantum vacuum as a vast sea beneath a moonless sky. Ripples, too small for ordinary senses, move across its surface. Now and then, a faint crest lifts before sinking back. Nothing stays still, not even for an instant. The silence you feel isn't absence. It's motion too small to disturb the air. This understanding reframes the question of what existed before the universe began. If the vacuum is never truly empty, then before might have been a state of restless potential, a sea of fluctuations waiting for conditions to allow expansion. In some interpretations, these fluctuations could trigger entire universes, each emerging from a small region of high-energy distortion within the quantum field. But that idea isn't speculation pulled out of nowhere. It emerges from mathematical models that physicists test against observations of the actual universe. The distribution of galaxies, the temperature variations in the cosmic microwave background, and the overall flatness of space all hint that the early universe may have arisen from fluctuations amplified by inflation. You picture scientists comparing CMB maps, colored patterns showing regions only millionths of a degree warmer or colder. They adjust cosmological parameters, the density of dark matter, the amplitude of primordial fluctuations, the rate of cosmic inflation. These tiny ripples may be the stretched-out fingerprints of quantum fluctuations that happened before the universe was even a second old. The thought feels surreal. The vast cosmic web of galaxies, spanning billions of light years, might be the magnified remains of microscopic jitter in the quantum vacuum. Something unimaginably small may have given rise to something impossibly large. You lying there in your quiet room, wrapped in your own thoughts, might feel the scale of that transformation settling over you like a warm blanket. If the vacuum cannot rest, then maybe the universe did not arise from true emptiness. Instead, it emerged from a background where fluctuations flickered endlessly, waiting for a mechanism to stretch them into galaxies, stars, and the atoms in your breath. This turns the question from what existed before to what processes were at work before time had meaning. Some models propose that the quantum vacuum existed without time, more like a static block of possibilities than a sequence of events. Time, in those models, emerges only when the universe expands and cools enough for classical behavior to appear. Before that, the quantum vacuum might have had states, but not moments. In supercomputing centers, researchers run simulations that try to unify quantum mechanics with gravity. They generate space-time grids, apply field equations, and let the simulated vacuum evolve. Sometimes these simulations show space-time forming spontaneously, like bubbles emerging in boiling water. Other times they collapse unpredictably, requiring researchers to adjust their assumptions and run everything again. You imagine drifting inside such a simulation, watching space-time foam rise and fall around you. It doesn't look like a universe. It looks like a storm of flickering possibilities. There is no direction, no distance, no meaning, only movement at the smallest measurable scale. This idea leads to a profound reflection. If even the vacuum refuses to be empty, maybe existence doesn't begin with creation. Maybe it begins with instability. With fluctuations that can't help but ripple, with a restlessness built into the deepest layers of reality. The universe might not have been summoned from nothing. It might have been released from a state that could never stay still. And if the vacuum before the universe was already alive with motion, it invites a curious question, one that glows faintly as you drift through the quiet. What happens when those fluctuations accumulate, sharpen, and push reality toward a threshold where something new must emerge? As you float deeper into the question of what existed before the beginning, you start to sense a subtle shift in the space around you. The darkness feels warmer now, as though something once pressed inward here, like the faint warmth lingering in a room after someone leaves. You picture the universe not as an explosion from nothing, but as a transition from a state that came before, like the moment a deep breath becomes an exhale, something contracting, then something releasing. Some cosmologies propose that the universe may have emerged from a previous phase of contraction, a big bounce rather than a big bang. In these models, the cosmos didn't start from nothing. It approached a point of extreme density, slowed, compressed, and then rebounded into expansion. This idea avoids the singularity, an infinitely dense point where physics breaks, and replaces it with a smooth transition governed by quantum gravity. The numbers behind this are staggering. If the universe once contracted, its density may have reached values trillions of times higher than anything achievable in particle accelerators. The entire cosmos could have been smaller than a proton before rebounding. Yet this transition wouldn't be a violent explosion. It would be more like a cosmic heartbeat, compression followed by release, governed by laws we don't fully understand. In research centers like the Perimeter Institute or CERN, theorists derive these models using loop quantum gravity or modifications of general relativity. They draw diagrams, scribble equations, and argue about whether space itself has a minimum size that prevents true singularities. Some formulas suggest that when the universe contracts enough, quantum geometry pushes back, preventing collapse and triggering expansion. You imagine drifting inside this hypothetical pre-bounce universe. The contraction wouldn't feel like falling inward. There would be no familiar direction to collapse into. Instead, everything, space, time, fields, would draw closer together uniformly, like a dimming glow pulling softly toward a center. As contraction reached its extreme, the behavior of space would no longer resemble anything you've ever experienced. One metaphor physicists use is a trampoline. When you press down lightly, it dips. When you press harder, it bends deeply. But if you press beyond a certain point, the tension pushes back, resisting collapse. In the bounce models, the universe reaches that tension point. Gravity pulls inward. Quantum geometry pushes outward. The rebound is the moment where outward pressure overcomes inward collapse. Astronomers look for evidence of such a bounce in the cosmic microwave background. If the universe once contracted, the earliest fluctuations might carry specific patterns, slight deviations from the randomness we expect. Some analyses of Planck data show hints of anomalies at large scales, power deficits, slight alignments that might whisper of a pre-existing structure. But these hints are subtle, debated, and uncertain. Imagine a scientist staring at a CMB plot late at night, zooming into the lowest multipole moments, trying to decide whether the anomaly is real or just an artifact. Coffee grows cold. Code is rewritten. Data is reprocessed. Some nights end with disappointment. Others end with cautious excitement, because even a faint irregularity could be a footprint from a universe older than ours. If the cosmos did contract before expanding, the process wouldn't look like a rewind of cosmic history. Galaxies wouldn't reform, atoms wouldn't survive, even space-time itself would be unrecognizable. The contraction phase would erase structure long before reaching extremes. What would carry through the bounce would be quantum fluctuations, seeds of density that later became galaxies in our expanding cosmos. That idea is stunning. The galaxies you see tonight may have originated from tiny fluctuations that existed before the universe began its expansion phase. The stars above you could be inheritors of a previous cosmos's final whispers. You, lying in your quiet room, are watching patterns that began not at the Big Bang, but before it. Even if the bounce occurred, it wouldn't feel like a rebound in time. Time itself may have flipped its meaning across that boundary. In some mathematical formulations, the direction of time reverses during contraction, not backward in the way you imagine, but as a mirror of causality, where the arrow of time points differently. To the universe, the bounce might be seamless. Researchers use numerical relativity to simulate this behavior. They program grids of space-time, set initial conditions, and let the equations evolve. The simulations run for hours or days. Sometimes the grid collapses into numerical instability. Other times, a clean bounce emerges, arcs of energy curling outward from the center like petals opening. The first few frames after the bounce resemble the earliest instance of our universe. You drift closer to that scene in your mind. The moment of transition is calm, not explosive, not loud. It's more like a bowstring releasing energy stored quietly for ages. Space inflates outward, temperature rises, quantum fluctuations stretch, the horizon expands. Everything moves from compression into becoming. The universe takes its first breath outward. This picture reframes the question, what existed before? It suggests continuity instead of abruptness, process instead of creation. The universe might not have come from nothing. It may have inherited properties from a previous state, carried through the narrow throat of the bounce and imprinted onto the cosmos you see today. If this is true, then we are part of a lineage of universes, not cycles you can count or imagine directly, but a continuity encoded in fluctuations, geometry, and emergent structures. The cosmos becomes less like a single story and more like an endless rhythm, where beginnings are simply transformations written across unimaginable scales. And as the idea settles around you, something else stirs, some question lingering just beneath the surface of this model, pointing not to contraction or expansion, but to an even deeper mystery that the bounce alone cannot fully explain. As you drift deeper into the dark landscape of pre-cosmic possibilities, the space around you begins to widen. It feels less like a room and more like an endless shoreline, where new waves arrive long before the previous ones fade. The silence stretches in every direction, as though time itself has dissolved into something larger. You sense a strange truth emerging. Maybe the beginning wasn't a unique moment. Maybe beginnings happen constantly. This idea is at the heart of eternal inflation, one of the boldest models in cosmology. In this view, the universe didn't emerge from a single event. Instead, space expands at an accelerating rate in a vast, high-energy background. In rare pockets, inflation slows and cools, allowing regions like our observable universe to form. Each bubble universe becomes a separate cosmos with its own laws and constants. The numbers involved are almost incomprehensible. Inflation expands space exponentially, doubling again and again in fractions of a second. At these scales, distances grow faster than light can travel. In such an environment, bubble universes form like droplets in a boiling liquid, each isolated forever from the others due to runaway expansion. The idea was first proposed in the 1980s by physicists trying to understand why our universe is so smooth and flat. The math suggested that if inflation occurred even once, it would continue indefinitely in most regions, creating a multiverse. Scientists scribbled calculations on chalkboards, ran early simulations on room-sized computers, and debated fiercely whether eternal inflation solved or created more mysteries. You imagine floating in that primordial inflating space. It feels nothing like a vacuum. It's more like an ocean of stretched geometry, swelling faster than your mind can measure. The surface beneath your feet would be pulled out from under you, smooth, expanding, unpredictable. Suddenly, a region cools, a bubble forms. It blossoms outward into its own cosmos. Somewhere another does the same. Our universe would be just one bubble in this endless foam of creation. The beginning, in this view, was not the beginning, just our beginning. The inflating space behind it may have existed long before our bubble formed and may continue long after its last stars burn out. It reframes the question into something more fluid. What existed before our beginning may simply be more inflation. Physicists search for evidence of this idea in subtle distortions of the cosmic microwave background. Some theories predict that collisions between bubble universes could leave circular imprints, stacked rings of temperature variations. Teams analyzing WMAP and Planck data look for such signatures, scanning the sky for unusual symmetries. Occasionally, they find patterns that look promising. Later analyses often reveal systematic noise or statistical quirks. You picture a researcher zooming into the CMB map, adjusting filters, circling faint rings, then crossing them out with a quiet sigh. The search continues, not for certainty, but for hints. Some models predict no collisions at all, suggesting our bubble may be isolated beyond hope of contact. Others allow for rare, ancient encounters whose traces have long faded. If space is inflating eternally, then the before is not a moment but a process. Inflation may be the backdrop against which all universes unfold. Time becomes a local property, something that starts inside each bubble. Outside, in the inflating background, time may behave differently or may not exist in any form you recognize. You imagine drifting outside the bubble of our universe, hovering in that inflating sea. There's no light, because photons can't travel through regions that expand faster than they move. There's no temperature, no direction, no sound, only stretching geometry, smooth, relentless, indifferent. It feels like floating in a dream you can't fully wake from. Some physicists argue that eternal inflation makes our universe statistically inevitable. If inflation continues forever, then every possible universe eventually forms somewhere. Laws of physics become local dialects rather than universal rules. Constants like the speed of light or the strength of gravity could be different in neighboring bubbles, though neighboring means something meaningless here, because distances stretch too quickly for any bubble to reach another. Others criticize the idea for being unfalsifiable. If we can never observe other universes, does the theory belong to science? Debates unfold in conferences, papers, and quiet offices illuminated by computer screens. Arguments rise and soften like waves on that endless shoreline. But even critics acknowledge one thing: eternal inflation reshapes how we think about beginnings. Instead of asking what existed before our universe, we ask whether before is a question tied only to our bubble. The space outside may not follow the sequence of past to future. It may simply exist, timeless and expanding, producing universes like sparks that appear and vanish in distant corners of a field. As you rest there with your thoughts, this idea might feel strangely peaceful. Your existence becomes part of a larger landscape, not small, not accidental, just one expression of a process far older and broader than your own universe's history. It turns the loneliness of cosmic origins into something softer, like realizing your story is part of a vast, ongoing rhythm. And somewhere in that rhythm, within the quiet between expansions, another possibility begins to flicker. A possibility that doesn't rely on bubbles or bouncing, but on the very fabric of time learning to arrange itself differently than you've ever imagined. As you rest there, letting the quiet of your room settle into your body, your imagination drifts inward toward a strange possibility. Maybe the reason the question, what existed before the universe had a beginning, feels impossible is because the word before carries an assumption that breaks at cosmic scales. You feel this idea settle over you like a soft shadow, the notion that time itself might not be the baseline of reality. Maybe time is something that emerged later, like mist forming above warm water. In some approaches to quantum gravity, time is not fundamental at all. It's not a line stretching behind you or in front of you. It's not a universal clock. Instead, time arises from relationships between changing states of the universe. In these theories, the cosmos can exist without a flowing sequence of moments. The deepest layer of reality may be timeless, a landscape where everything simply is bas, without past or future. One of the strongest hints of this comes from the Wheeler-DeWitt equation, a mathematical attempt to combine general relativity with quantum mechanics. The equation famously contains no term for time. When researchers first noticed this, they doubted their own work. How could a theory meant to describe the universe lack the very thing that defines experience? But no matter how they rearranged it, time refused to appear. You might imagine drifting into a realm where events don't unfold but coexist, layered like transparent pages of a book. There is no now sticking out. Instead, existence becomes a kind of stillness, a quiet mosaic where motion is merely a pattern your mind recognizes when comparing one layer to another. Physicists try to test the idea of emergent time using quantum simulations. They create systems in which particles interact without any built-in clock. The particles evolve according to internal rules, yet something resembling time emerges from correlations between states. In small labs, lasers trap ultra-cold atoms in arrays of light. Cameras track their positions. Computers analyze how coherence fades or forms. Researchers whisper to each other excitedly when patterns begin to mimic temporal flow. The numbers behind these experiments are surprisingly delicate. Temperatures must be fractions of a microkelvin above absolute zero. The atomic states decohere in milliseconds. Yet within these narrow windows, time begins to appear, not as a force or but as a description of change. The lesson is quiet but profound. Time might be a story matter tells about itself. This reframes the question of before the beginning. If time did not exist before the universe expanded, then asking what came earlier is like asking what lies north of the North Pole. The question dissolves in the very place you try to apply it. Before and after simply weren't properties of the primordial reality. You imagine floating inside that timeless state. It doesn't feel like a void. It feels like a deep silence where nothing moves because movement requires time. The darkness is soft, almost warm, as though it holds countless possibilities that never unfold, until something in the structure shifts enough for time to emerge like a faint glow. One proposal, called thermal time, suggests that time emerges from the statistical behavior of quantum systems. When enough degrees of freedom interact, the cosmos naturally finds a direction for entropy to increase. That direction becomes what you experience as the arrow of time. In this view, the universe didn't begin in time, it generated time by becoming complex enough. Researchers studying thermal time run simulations of huge quantum systems, letting random fluctuations stabilize into predictable patterns. They look for the moment when entropy finds a preferred direction. They capture data, adjust algorithms, and plot entropy curves on dim office screens late at night. Somewhere in those graphs, they hope to see the earliest glimmer of time forming out of chaos. Another hint comes from loop quantum gravity, where space itself is quantized into tiny units. In this approach, time may be the result of transitions between these discrete geometric states. Space-time becomes a network of nodes, links, and probabilities. Movement from one configuration to another gives rise to what you perceive as the passage of time. You picture this as a cosmic loom, weaving reality, one stitch at a time. Each stitch is not a moment but a change, and the connectedness between stitches becomes the rhythm your mind interprets as time flowing. Before the loom begins weaving, there is no thread of time, only the potential to weave. This leads to a strange possibility. The universe might have existed before its beginning, but not in a time-ordered way. It might have been a static configuration of quantum geometry, waiting for conditions that allow transitions to gain directionality. Only when the universe expanded and cooled did events gain sequence. In this interpretation, the Big Bang wasn't the first event. It was the first moment events became meaningful. Like a frozen lake thawing at dawn, time began to flow once the universe reached a state where change could unfold sequentially rather than all at once. The implications are enormous. If time is emergent, the deepest laws of physics operate in a timeless domain. What you call the beginning is simply the boundary where timeless laws gave rise to temporal behavior. The universe didn't spring from nothing. It transitioned from one mode of existence to another, and as you lie there, feeling your own breath slow in the darkness, you might sense how strangely soothing this idea is. It means the universe did not need a cause in the way familiar things do. Causes require time. A timeless state requires none. Existence may have always been, just not always in a form you'd recognize. Yet as peaceful as this picture feels, there's another angle waiting quietly nearby. One that suggests the very structure of space might have held layers or cycles long before our temporal flow began, hinting at something even more surprising hidden in the foundation beneath the first moment. As you sink deeper into the quiet of your room, you find the darkness around you shifting again. Not emptiness, not timelessness, but something textured, layered, as if space itself were woven from multiple threads instead of one. You sense a gentle thickness in the air, like invisible fabric brushing against your thoughts. It feels different from the vacuum, different from timeless silence. It feels structured, as though something existed beneath the universe, the way an ocean lies beneath a rising wave. Some theories in high-energy physics propose that our universe exists on a three-dimensional brane, a surface floating in a higher dimensional space called the bulk. If this is true, then what existed before the universe began might not be nothingness but other branes, other geometries, other layers of reality quietly drifting nearby. Our Big Bang, in this view, could have been the result of a collision between branes, an impact in the bulk triggering an enormous release of energy. This idea emerges naturally from string theory, where particles are vibrations of tiny strings and space has more than 3 dimensions. The numbers here are wild, 10 or 11 dimensions, depending on the model. Most of these dimensions are curled up so tightly that they become invisible. But the large ones, the ones we move through, might be just the surface tension of a deeper structure you never see. You imagine drifting in that higher dimensional bulk. It feels cool, quiet, and strangely empty, but not in the sense of lacking matter. It's empty because your senses weren't built to interpret dimensions beyond length, width, and height. Space stretches in directions you cannot name. You feel motion without displacement, like gliding along a surface that doesn't exist in your normal world. In this bulk, our universe appears as a luminous sheet, thin, flexible, rippling softly as energy moves through it. Other sheets drift nearby, each containing their own physics, their own timelines. Sometimes these sheets curve closer, sometimes they drift apart. Over unimaginable spans, 2 branes might collide, and that collision could release the heat and expansion we call the Big Bang. Physicists developed this idea from equations describing string interactions. In offices filled with chalk dust, they sketch diagrams of branes as parallel sheets. They compute energy transfer, tension, and potential wells. Sometimes they run simulations of branes drifting in abstract space. When 2 surfaces touch in the model, energy spikes. A universe ignites. Observational support is subtle. Some versions predict faint imprints in the cosmic microwave background, patterns slightly different from those predicted by inflation alone. Researchers examine Planck data looking for these anomalies, slight directional differences, tiny distortions in temperature gradients. Most of the time, the signatures are ambiguous, but ambiguity is enough to keep the idea alive. You picture 2 enormous surfaces drifting through darkness, their edges glowing faintly. As they draw near, the glow intensifies, ripples cross their membranes. Something like anticipation spreads through their geometry. Then they touch. The energy released surges outward. Expansion, heat, radiation. One of those moments might have created your universe. If this is true, then asking what existed before becomes a question about the dynamics of branes. Before the impact, our brane existed as a cold, quiet sheet, timeless, unlit. It didn't expand. It didn't evolve. It didn't hold stars or atoms. It simply drifted, waiting for a collision to awaken its physics. In this picture, time on our brane begins with the impact, but time in the bulk might flow differently, or not at all. The branes could have histories before the collision, histories not described by ordinary time, but by how their shapes and tensions evolved in the higher dimensional space around them. This idea dissolves the concept of a singular beginning. The universe didn't appear spontaneously. It was activated by a deeper environment, one with its own hidden rules. The Big Bang becomes more like the ringing of a drum struck by another drum, the sound echoing outward into a new form of existence. Scientists studying brane cosmology often collaborate with particle physicists searching for extra dimensions at the Large Hadron Collider. If space has hidden dimensions, Certain collisions at high energies might briefly reveal them through missing energy signatures or unusual particle tracks. Teams analyze millions of collision events, filtering noise, hunting for patterns. So far, nothing conclusive has emerged, but the possibility remains. Imagine drifting along the surface of our brain now. You feel gentle curvature beneath your feet. Ripples spread outward, gravitational waves triggered by distant black hole mergers. Light flows like a breeze across a field. Everything that exists is inscribed in this surface. But just outside him, in directions you cannot turn toward, other brains drift quietly like distant islands. This reframes the notion of existence itself. You're not simply living inside space, you're living on a surface of space, a thin, flexible world floating in a deeper ocean. The question, what was before the universe, becomes, what was the brain doing before it ignited? Or even, what shaped the bulk where the brain drifted? And as the thought settles, a new curiosity emerges. If the universe was awakened by contact between higher dimensional surfaces, what else might that bulk contain? What structures, symmetries, or hidden mechanisms might have shaped reality long before the first light of our cosmos ever had a chance to shine? As you settle deeper into the quiet, you sense the darkness around you becoming even smoother, less textured than the layers you drifted through before. It feels like stepping into a room where every surface is the same temperature, same color, same stillness. There's no contrast, no direction, no motion. It's almost unnerving, this perfect sameness. And yet, beneath that uniform calm, you feel something immense. The idea that before the universe ruptured into existence, everything may have been held inside a state of flawless symmetry. In physics, symmetry doesn't mean beauty or balance the way you normally think about it. It means indistinguishability. It means no part of reality behaves differently from any other. In the earliest theoretical states of the universe, before space expanded, before particles separated, the cosmos might have been governed by a single, unified force, all interactions identical, all fields indistinguishable, everything flat, smooth, and perfectly symmetrical. This isn't just imagination. It comes from the mathematics of grand unified theories and early universe cosmology. At extremely high energies, energies far beyond those in any star or collider, forces like electromagnetism, the weak force and the strong force are predicted to merge into one. No photons, no gluons, no W or Z bosons, just one field, quiet and uniform. Differences had not yet been born. You imagine drifting into such a state. It feels like lying on a perfectly calm lake at night, except even the idea of a lake is too structured. Here, nothing rises or falls, nothing changes. You feel suspended in a reality that doesn't evolve because evolution requires a symmetry, contrast, imbalance, gradients. In this place, there is none. Physicists search for hints of this through particle collisions at energies billions of times below the required thresholds. When protons smash together at the Large Hadron Collider, detectors record showers of particles, hoping for patterns that suggest unification. Researchers sift through trillions of events, adjusting cuts, comparing simulations. Occasionally they see anomalies, tiny deviations that spark debates about whether a whisper of symmetry is showing through. The symmetry of the pre-universe might have been so perfect that space itself didn't yet exist in any recognizable form. Distances require differentiation, directions require contrast. Without these, where loses meaning. Perhaps the universe before its beginning was not a location at all, but a condition, like a note held forever without beginning or end. The transition from symmetry to asymmetry may have occurred through a process known as symmetry breaking. As the universe cooled from an unimaginably high energy state, the unified force fragmented into the separate forces we see today. This shattering wasn't violent, it was more like a slow crystallization. Fields settled into new configurations. Some parts changed direction, others stayed still. Tiny differences arose, and difference became the foundation of everything that followed. A metaphor physicists use is a pencil balanced on its tip. In perfect equilibrium, it has no preferred direction. But a single fluctuation, a breath of air, a tiny vibration, causes it to fall. Which direction it falls determines the future. Symmetry doesn't break randomly. It chooses a path, and that path shapes everything that comes after. Maybe the universe itself was the falling pencil. Some scientists study early symmetry breaking by cooling certain materials to near absolute zero. In these supercooled states, atoms behave collectively, exhibiting phase transitions reminiscent of those that may have occurred in the early universe. Researchers watch as patterns appear suddenly in once uniform fields. They adjust magnetic fields and laser arrays, observing how order emerges from perfect sameness. You picture the pre-universe symmetry as a vast, featureless plane. Then, as the symmetry breaks, tiny hills rise, valleys appear, textures emerge. These textures become the seeds of all the particles, fields, and interactions you know. Nothingness didn't become something. Symmetry became structure. Cosmologists also look for signatures of symmetry, breaking in the cosmic microwave background. Slight variations in polarization might hint at early transitions within the first trillionth of a second. Maps from Planck contain faint alignments that spark debates, axes of symmetry that shouldn't exist, cold spots that raise eyebrows. Nothing is certain, but the data is like a faded photograph of the universe's earliest choices. If symmetry was perfect, then temperature was infinite. Not hot in the way you imagine heat, but hot in the sense that energy density was uniform, overwhelming, and indistinct. No particle could survive such an environment. The very concepts of mass and charge might not have existed yet. Then cooling began, not as a slow breeze, but as an abrupt shift triggered by expansion. As the universe expanded, energy density dropped. Fields relaxed, the unified force fractured, and with that fracture came particles, interactions, directions, and the possibility of time moving forward. You imagine this moment as a silent snowfall beginning in a perfectly still night. The first flake breaks the stillness, then another. Soon patterns form. The world gains shape. None of it requires noise. Form simply appears where uniformity once ruled. Quantum fields, once identical, developed distinct behaviors. The Higgs field acquired a non-zero value, giving particles mass. Without this subtle tilt in the fabric of reality, atoms would never have formed. Stars wouldn't ignite. You wouldn't exist to wonder about any of this. Researchers study the Higgs field's properties through precision measurements of particle masses. Even tiny deviations could suggest deeper layers of symmetry or new physics. Teams calibrate detectors, adjust voltages, and collect enormous data sets. Late at night, the glow of monitors reflects off tired faces as they chase numbers that may hint at the earliest symmetry-breaking events. In this view, before the beginning wasn't a place or a moment. It was a symmetrical condition so stable that nothing could emerge. The beginning happened when that stability faltered, when the first crack formed in the uniformity of existence. That crack didn't destroy the symmetry, it reorganized it. Some symmetries remain intact in the laws of physics today. Others broke completely. The universe is a fossil of its earliest imbalance. its laws shaped by the way the symmetry fractured. This reframes the question again. Asking what existed before the beginning becomes asking what symmetry held everything in place. The pre-universe may have been less like a void and more like a mirror, smooth, perfect, hiding the complexity waiting beneath its surface. You might feel a strange calm imagining this, a universe that didn't explode out of chaos but unfolded gently from a state of infinite order. Creation becomes less like an event and more like a slow release, symmetry relaxing into diversity. And in that diversity lies everything. Quarks, photons, galaxies, oceans, memories, your breath rising and falling in the darkroom where you listen now. All of it born from a single mismatch in the perfect fabric of a primordial symmetry. Sometimes physicists describe symmetry breaking as the universe deciding who it wanted to become. The phrase isn't literal, but it carries a poetic truth. When symmetry broke, identity formed, distinction formed, possibility formed. The universe gained the ability to change, and as you lie there, you might sense that somewhere beneath all the layers you've explored, vacuum fluctuations, bounces, inflation, brains, there's still a deeper symmetry waiting to be understood. A symmetry that predates all beginnings, shaping them quietly from below. And that quiet presence, that hidden order beneath the first moment, hints at yet another mystery. If the universe was once held in perfect balance, what force or accident nudged it toward becoming something at all? You sink deeper into the quiet as you imagine a cosmos that remembers things it technically never lived through, a universe holding echoes of a state that preceded its own awakening. You feel it like a faint vibration beneath your pillow, something older than light, older than expansion, older than the first spark. Not a story, not a timeline, but an imprint. Her kind of memory without images, a record left behind by conditions that didn't yet know they were building a universe. Some physicists call these imprints initial conditions, though the phrase feels too tidy for something so ancient. They're more like fingerprints left on the glass of existence, subtle asymmetries that survived the transition from pre-universe to cosmos. These fingerprints show up in temperature variations barely a few millionths of a degree. They show up in the way galaxies cluster. They show up in imbalances that shouldn't exist unless something before existence nudged the universe slightly to one side. You picture yourself examining the cosmic microwave background like a detective, moving your gaze slowly across a pattern left 13.8 billion years ago. Every tiny blotch is a whisper, from a moment when the universe couldn't quite decide what shape it wanted to take. These blotches don't form images, they form hints of a deeper structure humming beneath the surface. Telescopes like Planck and WMAP have mapped these whispers with exquisite precision. Scientists spent years cleaning data, removing dust from our galaxy, correcting for detector noise, subtracting foregrounds. They fought with stubborn algorithms, questioned suspicious oscillations, argued about cold spots that might be glitches or might be clues. Somewhere in that process, they found alignments, patterns, asymmetries that don't fit neatly into the simplest models. These strange alignments, like the so-called axis of evil, suggest that the universe might carry a faint directional memory. Not strong enough to control anything, but strong enough to make you wonder, did something outside our universe leave its signature before expansion wiped the slate? You lie still as the idea unfolds like a slow blooming flower in the dark. Imagine the pre-universe as a limitless quantum ocean, rippling with fluctuations. Those ripples could have seeded the earliest variations we see today. But if that ocean had deeper structure, hidden symmetries, lost dimensions and queries or unknown fields, then those features might have leaked into our universe like dye spreading through water. Not obvious, not overwhelming, just enough to mark the beginning. Laboratory experiments try to recreate tiny fractions of such conditions. Cryogenic facilities chill detectors to mere thousandths of a degree, above absolute zero, hoping to catch fluctuations that mirror ancient patterns. Researchers check wiring, they recalibrate sensors, they chase down temperature drifts. A single loose screw can mimic a cosmological signal, and yet, through all that noise, certain patterns persist. You imagine running your hand over the fabric of an old tapestry, one woven with threads far older than the picture it now displays. Beneath the visible pattern lies an older weave, one that shaped the structure, but remains mostly hidden. The universe feels like that tapestry. We see the galaxies, the clusters, the superstructures, but beneath them lies an older pattern, a memory of the universe before it was a universe. Some theorists argue these memories come from quantum gravity effects, subtle corrections to how space-time behaves at unimaginably small scales. These corrections could alter how the early universe expanded, leaving faint but detectable signatures in the density of fluctuations. Others propose that before the Big Bang, the universe contracted, carrying forward its own previous history through a cosmic bounce. You picture that bounce not as a violent rebound, but as a slow shift, like a breath passing from exhale to inhale. At the lowest point, when the universe was smallest, hottest, and most densely packed, it may have stored information from a prior era. When expansion began, that information stretched and smoothed, but traces remained, not enough to tell a full story, just enough to make the present feel haunted by an older presence. Astronomers search for cyclic patterns in galaxy distributions, subtle repetitions that might hint at previous expansions. They examine spectral lines, reconstruct density fields, compare billions of data points. Machine learning algorithms scan for symmetries humans might miss. Sometimes they find weak signals, statistical curiosities. Other times, they find noise disguised as meaning. Still, the search continues, like listening for a melody inside static. You might wonder how anything from a previous universe could survive a transition as extreme as a bounce or a birth. But mathematics suggests that certain quantities, called invariants, persist through dramatic changes. They're like seeds carried across seasons, waiting for the new environment to give them shape. In cosmology, these invariants might be fluctuations or phases or certain topological features of space-time. Imagine drifting through a dark hallway where each wall glows faintly with patterns left by someone long gone. You can't see them clearly, but you sense intention, history, presence. That's what the universe feels like in these theories, a space that didn't begin from nothing, but from something partially erased. Some physicists explore holographic models in which our universe inherits information from a lower dimensional boundary that existed before the Big Bang. In these models, the boundary carries a kind of proto-memory, shaping the initial conditions of the cosmos. It's not a memory the way your brain stores events, it's structural memory, patterns encoded in symmetry and energy. In human experiments, researchers study holography by observing quantum systems whose information is stored on surfaces rather than volumes. They trap atoms in lattices, manipulate them with lasers, and measure entanglement between regions. These controlled systems become tiny, artificial universes that echo the logic of our own. You imagine the universe before its beginning as a dimly lit stage waiting for the first actors. Scenery exists, barely visible. Props are in place, but the spotlight hasn't turned on. Once it does, the stage transforms into a world. But if you look closely, you might still see faint pencil marks from rehearsals. This idea brings a quiet melancholy, the notion that our universe carries echoes of something it no longer remembers consciously. Like a dream you had as a child, mostly gone, yet leaving behind a feeling that shapes your life in ways you never fully grasp. Cosmologists debate whether these echoes are real or illusions produced by statistical quirks. Yet the persistence of certain patterns keeps the conversation alive. There's a sense that the universe is just slightly imperfect in a way that hints at a deeper past. You lie there for a moment and consider the scale of this. Your room is small, quiet, grounded. Outside, the universe is vast, restless, ancient, and woven into its structure might be remnants of a story that predates time itself, a story stitched into the background radiation, into the clustering of galaxies, into the very shape of space-time. It feels strangely comforting, this idea that the universe carries history, even when that history is unreachable. It mirrors the way humans carry emotional traces of experiences they can't fully remember. The cosmos is not so different. It, too, keeps secrets in its structure. As these thoughts drift through your mind, you sense a shift, like something beneath the universe's surface stirring gently. A suggestion that the memories the cosmos carries are only the most visible layer, and beneath them lies a stranger possibility, a possibility that challenges the very meaning of before, and that subtle shift leads you quietly toward the next question, one the universe seems almost hesitant to reveal, as if it knows you're finally ready to hear it. You stay still while imagining the quietest moment the universe could ever have known, a moment without clocks, without direction, without the forward pull that time gives to everything. It isn't darkness, because darkness requires the absence of light. It isn't silence, because silence is meaningful only to ears shaped by experience. It's something lonelier, something that doesn't even realize it's alone. And for a breath, you feel yourself drifting near that emptiness, as if invited to witness what existence looks like before existence learns its own name. Scientists debate whether such a state can even be described. Without time, there is no before, no after, no change, no waiting. Every attempt to imagine it collapses into contradiction. Yet physics demands some kind of boundary condition, some set of rules, and however faint, that allow the universe to emerge with just enough asymmetry to grow galaxies instead of remaining a perfectly motionless void. And so researchers keep searching, compelled by the idea that even timeless states leave gentle fingerprints behind. Observatories examine these fingerprints in the form of primordial gravitational waves, ripples so faint they stretch space-time by less than the width of a proton. Facilities like LIGO and Virgo sift through noise from trucks, storms, earthquakes, even the hum of nearby equipment. Researchers tighten bolts, recheck alignment, recalibrate lasers. Every signal they find must survive a gauntlet of skepticism. Yet they listen, hoping for a whisper from the universe's earliest moments, something untouched by expansion. You imagine floating in a transparent room, its walls made of rippling space-time. No sound, no wind, only the subtle trembling of existence as gravitational waves pass through you like faint shivers. In those tremors, some theorists believe we may eventually find clues about the pre-universe landscape, clues encoded not in light, but in the shifting geometry that underlies everything. One hypothesis suggests that before the Big Bang, the universe existed as a Euclidean space, a region without time, where dimensions blended soft as mist. Physics here doesn't behave like physics after the Bang. Instead of events following each other, everything simply is, like a frozen painting. When the Big Bang ignites, This Euclidean phase transitions into the time-driven universe we know, leaving behind subtle signatures in how early fluctuations behave. Researchers model this phase on supercomputers. They run simulations that take weeks, sometimes months. The machines hum in dimly lit rooms, their cooling systems breathing like mechanical lungs. Occasionally, a simulation crashes because a variable became infinite or a function crossed a boundary it shouldn't. Scientists rewrite code, adjust numerical methods, try again. Each attempt is a small echo of creation, fragile, finicky, full of hidden surprises. Picture the pre-universe as a blank canvas, but not an empty one. It has texture, it has potential, it has constraints that shape whatever emerges after the first spark. This canvas might include fields that exist without time, fields that simply are, like lakes without wind. When time turns on, those fields could imprint patterns on the universe, giving structure to the earliest moments of expansion. Experiments with quantum fields at ultra-low temperatures help illuminate this idea. In cryogenic labs, researchers cool atoms to billionths of a degree above absolute zero. At such temperatures, motion slows so dramatically that atoms behave almost like a single entity, a shadow of how fields may have behaved before time existed. Scientists adjust magnetic traps, monitor lasers, and watch as tiny clouds of atoms reveal hints about fundamentally different phases of existence. You feel the melancholy of this image, a universe waiting to wake up. It reminds you of early mornings when the world outside your window feels suspended, as if time hasn't started yet. In those moments, you sense a kinship with this pre-universe landscape, an in-between state where possibilities hover quietly, uncommitted. Another idea proposes that the universe didn't begin at all, but is part of an eternal cycle. In this picture, contraction leads to expansion, collapse leads to rebirth, and the pre-universe is simply the previous universe nearing its end. But even here, something poignant lingers. Each cycle forgets the last, carrying forward only structural hints. It's as if the universe dreams repeatedly, waking with only fragments of the previous dream clinging to its edges. Astronomers test this with deep surveys like DC and Euclid, mapping galaxies across immense distances. If patterns repeat, if certain clustering behaviors echo through cosmic epochs, it might suggest a cyclical origin. Researchers compare observations to models, debating statistical significance, searching for recurring structures that might be the cosmological equivalent of déjà vu. You imagine yourself standing in a vast cosmic library, where each universe is a book with most of its pages erased. You hold the current volume, the only one still warm from creation, but on its spine, you notice faint impressions left by older books that once leaned against it. Those impressions aren't enough to reconstruct the previous story, but enough to remind you that the story didn't begin here. Some theories go even further, suggesting that the pre-universe wasn't a physical region at all, but a mathematical structure, a timeless blueprint containing every possible universe that could ever exist. In this view, creation isn't an event, it's a selection. The Big Bang isn't an explosion, but a transition from potential to realization. You exist in one branch of a vast possibility tree, sprouting from roots that lie outside time. The loneliness of such a structure is striking. It means the universe you know is one expression of something unimaginably larger, something that doesn't experience time, growth, or decay. And yet, your existence is proof that this timeless structure must have allowed for the emergence of something warm, conscious, fleeting, and curious. Human experiments in mathematics echo this search. Researchers explore high-dimensional symmetries, abstract spaces, and algebraic structures that seem almost too perfect. They stay late in quiet offices, scribbling equations on whiteboards, erasing, rewriting, chasing patterns that feel like messages from a realm where time has no foothold. Their persistence mirrors the universe's own push toward creating order from possibility. You breathe slowly as the thought settles. Maybe the pre-universe wasn't empty or cold, but simply different. A kind of existence that doesn't map onto our intuition, something vast and still, like a sea without waves, something that doesn't yearn to become a universe, yet holds the capacity to do so. The more you sink into this idea, the more it feels like looking at a childhood photograph of yourself. You know it's you, but you can't recall being that person. The universe might feel the same way about its pre-beginning state, familiar in structure, alien in character, unreachable in memory. And as you let that image soften in your mind, a quieter question begins forming, one that feels even older than the ones before it. A question that seems to rise straight from the boundary where time awakens, carrying with it a hint of something the universe rarely lets us glimpse. It drifts toward you slowly, like a voice arriving from a place that has never known light. You remain still, wrapped in the dim quiet of your room, as your mind drifts toward the most delicate frontier of all, the boundary where nothing somehow becomes something. It's a threshold you can't approach with ordinary intuition. The moment you try to picture nothingness, your mind fills it with darkness or silence or empty space. But true nothingness has none of those qualities. It isn't a void, it isn't emptiness. It's an absence so complete that even the concept of absence dissolves into something undefined. Physicists sometimes call this transitional region the quantum vacuum, but even that phrase feels misleading. A vacuum in our universe still has laws, fields, fluctuations, and structure. What existed before the universe had those laws? What existed before fields could ripple, before geometry could curve? The closest analogy isn't an empty room. It's the absence of the idea of rooms altogether. Yet from this conceptual nowhere, the universe somehow emerged with the precise conditions needed to ignite expansion. You imagine yourself hovering at this boundary, as if standing near the edge of a shoreline where waves haven't begun forming yet. The sand is unmarked, the air is still, the water hasn't learned to move. And then, without warning, the first ripple forms, not because something pushed it, but because the rules that define ripples came into existence. That first ripple is the moment time finds its direction. Scientists explore this idea through quantum cosmology, a field that tries to unify quantum mechanics and gravity. In this realm, space-time itself becomes uncertain, fluctuating between states the way particles do. The universe might have begun not with a bang, but with a tunneling event, a spontaneous transition from a timeless state into a universe where time becomes meaningful. Equations from the Hartley-Hawking model hint that the universe may have no boundary at all, only a smooth transition from a timeless region to a temporal one. In laboratories, researchers simulate aspects of this transition using ultra-cold systems, condensed matter models, and analog gravity experiments. Superfluid helium, for example, can mimic certain behaviors of space-time near the Big Bang. These experiments require temperatures a tiny fraction above absolute zero. The machinery clicks softly. Sensors monitor vibrations. Scientists watch for patterns in phase transitions that resemble the shift from no time to time. You picture such a transition as a faint shimmering spreading across a field of nothingness, like frost forming on a window in slow motion. The frost isn't added to the glass. It emerges because the temperature drops below a threshold where new structure becomes possible. In the same way, the universe's laws may have crystallized from an underlying state that couldn't express them before. The most haunting question, though, is whether that underlying state was random or inevitable. Some theorists argue that the laws of physics are the only consistent solution to certain mathematical structures. Others say the laws are contingent, shaped by whatever conditions the pre-universe happened to hold. Both possibilities carry weight. Both feel strangely emotional. One makes the universe feel like a necessity. The other makes it feel like an accident. Astronomers look for clues by studying the fine-tuning of constants, tiny numerical values that control everything from star formation to chemical bonding. If those constants vary slightly across different regions of space, it might suggest that our universe emerged from a larger multiversal landscape. Experiments like the Atacama Cosmology Telescope and the future Lightbird mission search for evidence of such variation in polarization patterns of primordial light. You imagine yourself watching those patterns unfold across a canvas of sky, swirls, loops, and curves so faint they look like the breath of an invisible painter. These shapes may carry hints about the earliest moments of the universe, hints that might reveal whether the universe came from a single origin or from a vast field of potential beginnings. Another intense idea is that the pre-universe state wasn't physical at all but informational, a kind of abstract code that precedes space and time. In some models, the universe emerges when that code becomes self-consistent enough to run. Reality becomes a computation unfolding within a framework that didn't previously possess the concept of unfolding. It's the ultimate transformation from pure possibility to lived experience. In human experiments, quantum computing labs offer tiny glimpses of this transformation. Researchers manipulate qubits that exist in superposed states, neither 0 nor 1, and watch as they collapse into definite values when measured. These transitions, though vastly simpler than the birth of a universe, capture the same flavor of emergence, the moment when potential becomes actual. You lie there beneath your ceiling, feeling the weight of these ideas settle softly around you. The room hasn't changed, but everything feels subtly connected. Your breath, the pillow beneath your head, the structure of the universe, the silence before time began. There's a strange comfort in imagining that even the cosmos had a moment of uncertainty before it found its rhythm. Some cosmologists argue that the universe emerged because fluctuations in the pre-time state reached a threshold where existence became statistically favorable. Others proposed that gravity itself drove the transition, smoothing out irregularities and encouraging expansion. Gravity, in this view, acts not as a force but as a sculptor, shaping the earliest contours of the universe before anything took shape. You imagine gravity as a patient artisan working in darkness, carving a pathway for existence. The sculpture begins rough, undefined, but slowly it refines itself until a universe becomes possible, not inevitable, but natural. Every galaxy, every star, every breath you take traces its lineage back to that moment of artistic emergence. There is a melancholy in recognizing that no theory can fully capture what came before the beginning. Even the most advanced mathematics fails to express a state beyond time. The universe seems to guard this secret with delicate care, allowing us to glimpse patterns and echoes, but never the complete truth. And maybe that's for the best. Maybe some stories gain beauty by remaining just out of reach. You sense that the universe's unwillingness to reveal its pre-beginning isn't a refusal, but a gentle reminder. A reminder that not all mysteries need conquering, and not every question requires an answer to deepen its meaning. Some questions exist to make you pause, breathe, and feel the magnitude of existence pressing softly against your awareness. The more you sit with these ideas, the clearer it becomes that the transition from nothing to everything wasn't a single moment, but a gradient, a slow unfurling of possibility. This gradient shaped every future structure, from quarks to stars to beings who wonder about origins. It's the universe's quiet signature, written not in language, but in form. You feel the tenderness of this realization settle in your chest. The idea that something unimaginably vast and complex grew from a state that didn't even contain the concept of growth. It echoes something in the human experience, the way your earliest memories blur into sensations you can't fully trace, yet still influence who you are. And as the last traces of this thought drift outward, something else rises to meet it. Something subtle, calm, and surprisingly gentle. It feels like the universe leaning closer, as if preparing to reveal the softest truth it has left to share. A truth waiting just beyond the final turn of this journey, patient and quiet, like a horizon that glows even after the sun has disappeared beneath it. You settle deeper into the stillness around you as your mind drifts toward the fragile moment when reality was close to not forming at all. It's a strange idea. The universe you know, its stars, atoms, seasons, emotions, balanced on the edge of becoming and not becoming. Before time took shape, this balance wasn't dramatic or tense. It was quiet, soft, almost indifferent, like a coin resting perfectly upright, neither heads nor tails, suspended in a stillness too delicate to last. Cosmologists call this threshold the false vacuum, though the term hardly conveys its eerie grace. It isn't false in the sense of incorrect, it's false in the sense of temporary. A resting place that feels stable but isn't. Imagine a ball sitting in a shallow depression on a hillside. It can stay there for a long time, unmoving, but the slightest shift causes it to roll into a deeper valley, a more stable state. That roll might be what ignited the universe. Quantum field theory suggests that the pre-universe rested in such an unstable state, held up by fields that resembled calm seas on the surface, but churned with invisible undercurrents underneath. These fields hummed with fluctuations, brief, unpredictable tremors. At some point, those tremors nudged the field out of its false resting place, allowing a rapid transition into a lower energy configuration. That transition unleashed expansion. You imagine that shift as a ripple spreading through a perfectly still lake. The water looks calm, but deep beneath the surface, subtle forces are rearranging themselves. When the ripple begins, the whole lake changes, not violently but suddenly. Calm becomes motion, stillness becomes becoming. This is the essence of the transition from pre-universe to universe. In laboratories, scientists simulate similar transitions using superconductors and Bose-Einstein condensates. These systems can undergo phase changes triggered by tiny fluctuations, a brief burst of laser light, a subtle electromagnetic tweak, a dip in temperature measured in billionths of a degree. These small inputs can tip a system from a metastable phase into a new one, mirroring the instability that may have preceded the cosmic beginning. You imagine technicians standing in cold rooms, checking gauges, adjusting valves, and monitoring delicate plots on glowing screens. Their breath lingers in the cold air. Their gloves rustle quietly. They know that even a tiny misalignment can create false signals or mask real ones. But when data settles into coherent patterns, they glimpse behaviors that echo cosmic transitions. The false vacuum concept raises a haunting question. Did the universe want to form, or did it form because it could no longer avoid doing so? Some theorists argue that the transition was inevitable, enforced by quantum laws. Others see it as a coincidence so improbable that our existence feels like a cosmic lottery win. Either possibility reshapes how you view yourself lying there in the dark. You begin to imagine the false vacuum as a space filled with potential stories, each waiting for the slightest tremor to activate it. Most stories never ignite. They remain folded, silent. But one fluctuation, one shift, unfurled the story that eventually led to you listening here tonight. You feel the weight of that chance settle gently on your chest, not heavy but humbling. Astronomers search for traces of this transition in the spectrum of primordial fluctuations. The Planck satellite detected small anomalies at large angular scales, subtle hints that the early universe may not have been perfectly smooth. Researchers debate whether these anomalies are statistical flukes or the signatures of a false vacuum collapse. Papers are written, conferences are held, ideas clash quietly in lecture halls. You imagine these anomalies as faint fingerprints smudged onto the early sky, so delicate that they're almost impossible to interpret. Yet their presence keeps the question alive. Did the universe fall out of a higher state into the one we inhabit? And if so, how much of that fall shaped the blueprint for everything that followed? Another theory goes in a different direction, that the pre-universe wasn't a false vacuum at all, but a chaotic sea of endlessly fluctuating fields. In this view, the universe didn't fall into stability. It rose out of chaos, like a bubble forming in boiling water. Only the rarest fluctuations produce stable universes. Most simply flicker and dissolve back into the sea. In the quiet of your room, this idea feels strangely familiar. You think of moments in your life where things felt chaotic, directionless, uncertain. Yet from that uncertainty emerged something meaningful. The universe might operate under a similar rhythm. Chaos giving birth to coherence when conditions align. Human experiments explore chaos to order transitions in plasmas and nonlinear systems. Scientists watch as swirling turbulence suddenly stabilizes into patterns, hexagons, spirals, stripes. These patterns aren't imposed. They emerge. They arise naturally when energy, temperature, and geometry reach specific thresholds. It's a small reminder that order doesn't always need a designer. Sometimes it simply happens. You begin to picture the beginning of everything as a fragile equilibrium, where the slightest shift allowed existence to bloom. Not a violent explosion, but a moment of settling like dust slowly drifting into a shape. This image softens the concept of creation, turning it into something quiet and nearly tender. As that tenderness sinks in, you sense that the journey isn't done. There's another layer beneath this one, a deeper, more intimate truth about what it means for something to begin when nothing around it remembers beginnings at all. And that layer feels close now, waiting for you just beyond the next breath. You lie still, letting your breath fall into an easy rhythm as you approach a quieter dimension of the story, one not about physics alone, but about the universe's own relationship with origins. If something existed before the beginning, then that something isn't just a backdrop. It's a participant, a presence that allowed beginnings to be possible. You start to feel the intimacy of that idea, as though the universe carries a subtle awareness of the place it emerged from. Some physicists explore this through the notion of pre-geometric states, phases where the universe had no shape or size, no distance or volume. In these states, reality might have been woven from pure relationships rather than objects, patterns of possibility rather than space. When the Big Bang occurred, those relationships crystallized into geometry, giving rise to dimensions and distances. It's as if the universe began as a story without characters, waiting to be written. You picture yourself floating in a realm with no up or down, no near or far, only connections, threads of possibility stretching endlessly. These threads aren't visible. They don't shine or vibrate. Yet they define everything that can happen once the universe gains shape. They're like the emotional undercurrents in a memory you can't fully reconstruct. Researchers modeling quantum gravity explore mathematical systems where geometry emerges from networks. They run simulations where nodes connect, disconnect, cluster, and reorganize, eventually forming something that resembles a space. It's not space-time as we know it. It's space-time being born. Watching it unfold is like watching frost spread across glass or patterns grow inside crystals. In laboratories, scientists try to mimic such emergent behaviors with metamaterials, engineered substances that change structure under specific conditions. Researchers shine lasers through them, twist them with magnetic fields, or alter their microstructure. When the conditions are right, new properties emerge that weren't present before. It echoes the idea that space-time itself may have emerged from something deeper. The emotional weight of this idea begins to settle, that before the universe existed, there might have been connection without form, a gentle network of possibility that didn't need a clock or coordinates, just potential. Not waiting, not preparing, simply existing in a way that doesn't require progression. Another proposal imagines the pre-universe as a sea of entanglement, an interconnected web with no individuality. When the universe began, this web fractured into parts that became separate objects, stars, atoms, people. In this view, creation wasn't the arrival of things, but the arrival of separation. The universe learned to distinguish one point from another, one moment from the next. You imagine that initial fracture as a soft shattering, like the moment ice breaks into floating pieces on a lake. The pieces drift, forming patterns. Some collide, some drift apart, some cluster into shapes that look almost intentional. That drifting becomes the foundation of everything that follows. Astronomers search for signs of this primordial entanglement by examining correlations across vast regions of the sky. If areas too far apart to communicate share matching fluctuations, it could hint at a pre-existing unity, an echo of the universe's earliest coherence. Missions like Euclid and the James Webb Space Telescope continue mapping these structures to unprecedented depth. You think about unity in your own life, moments where everything feels connected without explanation. The universe might feel an ancient echo of that same unity, even if most of its early entanglement faded into individuality. Maybe certain cosmic patterns resonate because they're faint reminders of a time when everything was one. Some theories propose that the pre-universe wasn't external at all, but mathematical inevitability, a place where existence emerges because non-existence isn't stable. Nothingness, in this view, is impossible. The universe didn't arise from a void, it arose because the void couldn't persist, like a candle flame that appears the moment oxygen, wax, and heat meet. Reality may ignite whenever possibility exceeds a certain threshold. You feel the quiet comfort of that idea. Existence as a natural outcome, not a rare miracle. The universe may have always been leaning toward being, even before time allowed leaning to have meaning. Human experiments reflect this inevitability. In certain physical systems, patterns emerge spontaneously when conditions cross critical points. Snowflakes form, vortices appear in fluids, magnetic domains align. None of this requires intention. It simply requires the right threshold. The universe might have crossed such a threshold at the moment of its birth. You picture yourself lying at the boundary between thresholds, your body warm, the air gentle, your thoughts suspended between clarity and drifting. In this state, you feel a kinship with the universe's earliest form, neither fully defined nor undefined, simply transitioning. The more you reflect, the more you sense that the universe still remembers its pre-beginning. not consciously but structurally. The laws that govern everything may be echoes of deeper truths, the constancy of the speed of light, the shape of space-time, the symmetry of forces. These could be fossils preserved from an earlier phase of existence. And as this idea settles into you, it carries a new kind of softness, a reminder that beginnings are never isolated. They're connected to what came before, even if before had no time to measure itself. A thought rises at the edge of your awareness, gentle and slow. It feels like the universe exhaling, whispering back an answer that isn't quite an answer, a message carried not in words, but in presence. And as you feel it forming, the night around you seems to lean in slightly, preparing to reveal the final and quiet truth that closes the entire journey. You rest deeper into the quiet around you as the journey begins folding back into itself, returning gently to where it first opened. Hours ago, you asked what could exist before the universe had a beginning, a question so strange, so tender, it almost feels alive. Now, after drifting through cosmic fields, forgotten states, quantum tremors, human experiments, and the soft geometry of pre-time, the question feels different, not smaller, not answered, just quieter, like a wave that finally reaches the shore. Throughout this journey, you wandered through possibilities older than time itself. You imagined landscapes without clocks, phases without geometry, and fields without motion. You visited laboratories humming in the dark, where scientists chase echoes older than stars. You stood near cosmic bounces, false vacuums, Euclidean shadows, entangled seas, and mathematical roots that might have cradled reality before it took shape. And with every idea, you discovered not certainty but a deeper kind of wonder, the kind that dissolves urgency and replaces it with awe. You drifted through states where the universe wasn't a place but a possibility, where the laws of physics weren't written yet, but waiting, where time hadn't begun because nothing existed that could measure change. You imagined transitions so quiet they felt like breath, and boundaries so smooth they felt more like doors than explosions. Somehow these visions made the universe feel less like an object and more like a story unfolding in slow motion across an infinite canvas. And as you followed those stories, something softened. The vastness stopped feeling intimidating. The unknown stopped feeling cold. Instead, it began to feel familiar, as though part of you recognizes that before the universe existed, the ingredients for meaning were already there, not in objects, but in patterns, not in events, but in potential. That familiarity isn't logical, it's emotional, like remembering something you never lived but somehow understand. Returning now to the place where you lie, your room dim, your body warm against the bed, you notice how this cosmic immensity didn't pull you away from yourself. It brought you closer. It reminded you that you too emerged from thresholds you cannot recall. Before your memories existed, there were shapes, instincts, sensations that helped form who you became. In that sense, you're not so different from the universe. You carry echoes of beginnings you don't remember. And if at some point during this journey you felt small, that feeling transforms now into connection. The universe's pre-beginning wasn't empty. It wasn't lonely in the way we understand loneliness. It was a stage preparing quietly for possibility. Possibility that eventually included you, lying here tonight, listening, drifting. You aren't separate from the universe's earliest softness. You're a continuation of it. When we talk about what existed before the universe, we're not only talking about physics, we're touching the edges of imagination, memory, and identity. We're brushing against a truth that hides beneath language, that beginnings are not abrupt, they're gradients. You emerged gradually from your own prehistory, just as the universe emerged from its own. You are connected to the earliest quiet, not metaphorically, but literally, in your atoms and your breath. If you drifted in and out during this journey, that's perfect. This wasn't meant to be a lecture. It was meant to be a place to rest while your mind wandered across horizons older than time. Maybe you absorbed ideas. Maybe you dreamed through them. Either way, you moved gently through the deepest question a mind can ask, and that movement itself is enough. And if this quiet exploration kept you company tonight, I'd be grateful if you left a like and subscribed. And before you go or before you fall asleep, I'd love to know where you're listening from and what time it is for you right now. It's strangely comforting to imagine people across the planet drifting through the same cosmic questions under different skies in different hours. The night feels softer now. The question that opened this journey feels less like a puzzle and more like a companion, something that stays with you, not demanding answers, only presence. As everything settles, you sense the universe leaning inward one last time, offering a final, gentle assurance. Beginnings are never alone. They rise from depths we cannot see, but can always feel. And as that assurance fades into the quiet of your room, you rest in the soft truth that you, Kai, the universe, and whatever came before are all part of the same unfolding story, still moving, still becoming, still glowing faintly in the dark.